This is the third part of the Week 4 overview, concentrating on the last two sections of the reader, sections 9 and 10. We've already talked about the shape of the sampling distribution for proportions very informally when we looked at figure 13.5 in Baldy and Moore. They say that the distribution of the proportion p hat of successes is approximately normal, and for small samples this is not always true. So this illustration is a little bit optimistic. The question we want to talk about is how large does the sample size n have to be for the central limit theorem to work for binomial counts and proportions p hat. Now we know that we are going to set the counts and proportions up as sums and averages of random variables, so the central limit theorem has got to apply in some fashion to these. But this is a trickier situation. What we're going to see in the material in the last part of week 4 is that the shape of the sampling distribution of p hat depends on both the sample size n and the population p. Just to give you an overview of what's coming up, the usual condition to trust the normal approximation for counts and proportions is that the expected number of yes n times p and the expected number of no n times 1 minus p have to both be at least 10. Section 9 has the title Normal Approximation to the Binomial, and when people say that, they mean the normal approximation to the binomial for counts. This is mostly of historical interest, and I want you to have some exposure to this material so you can decide if you can trust results that use it. Software makes it a lot easier to do inference for counts and proportions without relying on the normal approximation, but sometimes the normal approximation is okay. Here's a typical example. This is a normal approximation distribution for counts with an n of 100 and a population proportion p of 0.20. So this spike plot of the probabilities really does look similar to a normal curve, and we're going to have a contrast to that. We're going to keep the sample size 100, but now we're going to look at a fairly rare success, or yes, a proportion of 0.02 instead of 0.20. And you know what? Even for n equal to 160, the tails of the distribution don't look symmetric. It's only the picture in the lower right-hand corner where n is equal to 640 that the distribution for the number of yes looks similar to the normal curve. So this is what I mean by saying that the application of a normal approximation for counts depends not only on the sample size, because certainly a sample of size 320 sounds pretty large, but it also depends on whether we're looking at a very rare event. There's something we're going to talk about in our work with the normal approximation to the binomial that's called a correction for continuity. And what we mean by that is the binomial is actually a discrete distribution. That's why we've been using spike plots like this. So if you take a look at this binomial distribution with an n of 100 and a p of 0.40, the probability that the count is equal to 49, pretty small, but it's a positive number, 0.0152. But for a normal curve, like any continuous distribution, we're forced to say for a normal curve, the probability that x is equal to 49 exactly has to be 0, because normal curve areas don't exist if there's not an interval. So to approximate binomial probability spikes with normal curve areas, we'll say things like this. To approximate the binomial probability x is equal to 49, we'll use the normal curve area between 48.5 and 49.5. And if you have to do the normal approximation to the binomial for counts, this kind of correction to bridge the gap between the continuity of the normal curve and the discrete binomial distribution gives us better answers. So here's an example that we're going to look at. We actually took a look at this earlier in week 2 when we were talking about binomial probabilities. This is an exercise from Baldi and Moore that looks at post-menopausal women and low bone density. Population proportion assumed to be 0.40 for a certain practice with 248 post-menopausal women. They only had 82 with low bone density. So we already used this to illustrate Stata's binomial function. Probability of 82 or less using the binomial function is about 0.0145. The conditions to use the normal approximation are going to be satisfied here. So let's see what we get. Number of expected yes, n times p, 248 times 40 is 99.2. Number of expected no, n times p, 248 times 60, 148.8. So these are both much greater than 10. So the conditions for the normal approximation are going to be okay. We already know the mean, n times p, 248 times 40, the expected number with low bone density, 99.2. We need to work out the variance, n times p times 1 minus p, 248 times 0.40 times 0.60 is about 59.5. So when we take the square root for the standard deviation, we're going to get 7.7. So if we use the continuity correction to take a look at our practice's results, we're going to be working out x less than 82.5 for a normal curve with the mean of 99.2 and a standard deviation of 7.7. And so the z-score is going to be 82.5 minus 99.2 divided by 7.7. It's about a negative 2.17. The area below minus 2.17 is about 0.015. So that lines up pretty well with what we got from the binomial. So bottom line is the normal approximation is okay, but it's never really necessary. Now we're also going to be looking at normal curves for p hat. Here's the problem from Baldi and Moore, 1311 and 1333. It's one of those apply your knowledge problems in the middle of the chapter. They ask you to work with an n of 150 and a p of 0.06. And I don't think that's too wise because 150 times 0.06 is 9, and that's kind of less than 10 for the normal approximation. So I kind of changed the problem around a little bit in the reader to have an n of 500, a sample number of yes of 18. And here the conditions would work out. We're going to look at some questions. Are we going to get a sample p hat of 0.036 if the population proportion is really 0.06? I'm a little more comfortable using the normal approximation here than in the original problem they set out. So you can do this using a counter of proportion. If you want to do the binomial function, just use the count of 18. If we're going to do a normal approximation, we're okay now with an n of 500 and a p of 0.06 because the expected number of yes is 30. Expected value of p hat is still stated as p of 0.06. The standard deviation of p hat is going to work out to be p times 1 minus p over n, all square rooted, 0.06 times 0.94 divided by 500. Sample size is pretty large, so we can take the square root of that and get 0.0106. So here's the z-score for our observed proportion, p p hat of 0.036 minus 0.06 divided by that standard deviation, we have a pretty low z-score. It's about minus 2.26. The area under the normal curve is about 0.012. The exact binomial gives, for x less than or equal to 18, about 0.011. So yeah, the normal approximation works here. You still don't have to use it. And we're going to find the normal approximation for p hat useful for doing inference problems. So that's more important than the approximation for counts. So what should you be focusing on in this last part of week 4? I think the applied problems for the behavior of averages, p hat, are the most important thing to work with. The mean and variance of the population of p hat values are p, and p times 1 minus p over n. And again, parallel to what we did when we were working with averages, these facts about the mean and variance of p hat are always true for any n. It's the normal curve question that requires very large samples sometimes for the central limit theory. So again, the sampling distributions of counts and proportions are approximately normal when we look at the expected number of yes, n times p, and the expected number of no, n times 1 minus p. They both have to be at least 10. We can always use the binomial functions for these kinds of calculations. The normal approximation is sometimes useful, particularly for inference problems. And when we work through the material in weeks 5, 6, and 7, we will be sure to cover some inference techniques for population proportions when the normal approximation does not hold. Stata will make that easy to do. So if this has seemed pretty straightforward, you don't need to watch the narrated PowerPoints in sections 9 and 10. They use some of the same examples and repeat some of the reasoning, partly because we found in the past that students liked that additional narration rather than looking at the reader and wanted a little more than in the overview. So be of good cheer at this point. You've almost made it through all the week 4.